children. I am Shushmita and welcome back to another video. Previously, you have learned about direction of the magnetic field. Now, in this video, let us gather some information on Fleming's left hand and right hand rule. Learning outcomes. At the end of this session, you will be able to understand about magnetic force on moving charge, force on a current carrying conductor in a magnetic field, Fleming's left-hand rule. Fleming's right-hand rule. Keywords. Magnetic field, the region around a magnetic material. Force, current, moving charge, conductor, a material that allows electricity to flow through it. Fleming's left-hand rule. Fleming's right-hand rule. Before starting this session, let us look at the concept map of today's session. To understand the concept of the magnetic force on a moving charge, let us consider an activity. Take a bar magnet and bring it near the TV screen. You can observe that the picture on the screen is distorted. Why does the picture get distorted? Is the motion of electrons reaching the screen affected by the magnetic field of the bar magnet? Move the bar magnet away from the screen. Now you will get a clear picture. Repeat this to confirm that the motion of electrons is affected by the magnetic field produced by the bar magnet. This must be due to the fact that the magnetic field exerts a force on the moving charges. This force is called magnetic force. To calculate the force experienced by a charge moving in a magnetic field. Let us consider a charge Q moving with a velocity v perpendicular to the magnetic field B. The magnetic force acting on a charge Q is F is equal to Q V B and holds well only when the direction of the velocity of the charged particle V is perpendicular to the direction of the magnetic field B. It is experimentally proved that when there is an angle between the direction of field and velocity, the magnetic force experienced by the charge is given by F is equal to Q V B sin theta. When the charge moves parallel to the magnetic field, along the magnetic field or against the field, the value of theta becomes 0 in F is equal to Q V B sin theta, so that sin theta is equal to 0. Thus, the charge experiences no force when it is moving parallel to the magnetic field. Along field direction or against field direction. An easy method to find out the direction of magnetic force acting on a charge moving in a magnetic field is by using Fleming's right-hand rule. Generally, the right-hand rule is used when velocity and field are perpendicular to each other. According to this rule, stretch the thumb, forefinger and middle finger of your right hand such that they are mutually perpendicular. The middle finger points towards the direction of the velocity of charge or current. The forefinger points to the direction of the field. B. The thumb gives the direction of force. We have learned that an electric current flowing through a conductor produces a magnetic field. The field so produced exert a force on a magnet placed near the conductor. French scientist André-Marie Ampère suggested that the magnet must also exert an equal and opposite force on the current carrying conductor. Let us understand the concept of the force due to a magnetic field acting on a current carrying conductor. by considering an activity. Take a small aluminium rod AB and suspend it horizontally from a stand using two connecting wires. Place a strong horseshoe magnet in such a way that the rod lies between the two poles with the magnetic field directed upwards. To make the magnetic field directed upwards, put the north pole of the magnet vertically below and the south pole vertically above the aluminium rod. Connect the aluminium rod in series with a battery, a key and a rheostat. Now pass a current through the aluminium rod from end B to end A. We observe that the rod is displaced towards the left. Now reverse the direction of the current flowing through the rod. We observe that the rod is displaced towards the right. The displacement of the rod suggests that a force is exerted on the current carrying aluminium rod when it is placed in a magnetic field. It also suggests that the direction of the force is also reversed when the direction of the current passing through the conductor is reversed. Now change the direction of the field to vertically downwards by interchanging the two poles of the magnet. It is once again observed that the direction of the force acting on the current carrying rod gets reversed. It shows that the direction of the force on the conductor depends upon the direction of the current and the direction of the magnetic field. The displacement of the rod is largest when the direction of the current is at right angles to the direction of the magnetic field. In such a condition, we can use a simple rule called Fleming's left-hand rule to find the direction of the force on the conductor. We considered the direction of the current and that of the magnetic field perpendicular to each other and found that the force is perpendicular to both of them. The three direction can be illustrated through a simple rule called Fleming's left-hand rule. According to this rule, stretch the thumb, forefinger and middle finger of your left hand such that they are mutually perpendicular. If the forefinger points in the direction of the magnetic field and the middle finger in the direction of current, then the thumb will point in the direction of motion or the force acting on the conductor. Points to remember. The magnetic force acting on a charge Q is F is equal to Q V B. Fleming's right-hand rule states that if we arrange our thumb, forefinger and middle finger of the right hand perpendicular to each other, then the thumb points toward the direction of the magnetic force. The forefinger point toward the direction of the magnetic field. And the middle finger points towards the direction of the current. According to Fleming's left-hand rule, stretch the thumb, forefinger and middle finger of your left hand such that they are mutually perpendicular. If the forefinger points in the direction of the magnetic field and the middle finger in the direction of current, then the thumb will point in the direction of motion or the force acting on the conductor. The direction of the force on the conductor depends upon the direction of the current and the direction of the magnetic field. Thanks for watching this video.